Oops. Okay. Today's lesson is obviously the beginning of chemical bonding. Listen up. As we continue through our discussion on, and really this entire unit is called Properties of Solids, which is kind of interesting. In the end, what we want to be able to do is talk about why various types of compounds exist as solids at various temperatures. So like obviously water is a liquid at room temperature, yet if we have something like sodium chloride, it's a solid at room temperature, and if I've got something like oxygen gas, it's a gas at room temperature. So ultimately we want to talk about substances and the way we perceive their particular properties, typically at room temperature is what we want to talk about. So it ultimately comes down to atoms and the way they bond, and then the way those molecules stick together, intermolecular forces. So in the end, it's going to be all about intermolecular forces. This is really the same path that we took last year. We talked about atoms and Bohr diagrams, and then Lewis diagrams, and ions, and ionic compounds, and then covalent compounds, and then the intermolecular forces, the forces that hold these molecules together. And then we didn't go into detail about what properties they would manifest themselves as. So that's really the extension on this. In terms of intermolecular forces, I don't know if anybody has seen my website. I did a little update on it. I got rid of the volleyball, or not the volleyball. I got rid of that. I got rid of, see, like that? Very nice. Right? I got rid of the acid-base thing. That's an intermolecular forces thing. It's hydrogen bond right there. It's beautiful. All right. Okay, so today we're going to talk about ionic bonding. Just as we did last year, I talked about the fact that ionic bonding is very simple to explain. It's a transfer of electrons, and then we will move on to covalent bonding, which is quite complex. We won't be going over the naming, right? Last year we talked about ionic bonding, and then we took 3 or 4 days to talk about the naming of ionic compounds. We are not reviewing naming in this course. We're going to assume that you guys have the fundamentals of the naming system. And we've been using it up to this point anyway. So ultimately, it's electrostatic forces that hold atoms together in compounds. In an ionic bond, we've got that metal-non-metal situation. Electrons are completely transferred, resulting in oppositely charged ions, which then stick together in a lattice structure. And then covalent compounds, the electrons are shared. And again, we're going to maintain that very simplistic view, ionic, a metal and a non-metal, covalent, all non-metals. I indicated to you yesterday, if you continue on in chemistry, you will find that we can have metals actually covalently bonding with some non-metal structures in various types of complexes. They're called a complex. And so we can have covalent bonds between metals, but that's not the scope of this particular course. But like I said, if you continue on, you will learn that yeah, metals can get involved in bonding. Tends to be their d orbitals that get involved in that. But we will not be dealing with that. So, Lewis theory of bonding, we're going to be looking at 3 theories to explain bonding. We've already seen the Lewis theory, where we can draw a Lewis diagram to explain how the electrons are either traded in terms of ionic or shared. And the Lewis theory deals with this 8 this idea of an octet. On Monday, when we talk about covalent bonding, you'll be introduced to another theory. It's called valence bond theory, and that deals with our orbitals and how the orbitals interact. We will still be talking about orbitals in this case in today's examples. We'll also be drawing Lewis diagrams. So the Lewis theory, it kind of slightly predates this idea of orbitals. It has to do with this observation that chemists made that when atoms share or trade electrons, there's this underlying drive to get 8 electrons in the outer shell, whether it's achieved by losing electrons or gaining electrons. There's this drive to have 8 electrons. We can extend this now to what we now know about orbitals. We can extend it to the idea of either filling s and p orbitals, which total 8, or emptying out the s and p orbitals so that you've got that empty sp scenario. So right there where it says S and P sublevels are either full or emptied, that's how we can link our new idea of orbitals to the old idea of the octet, which we learned that last year. Lewis diagrams, even though they're a little more simplistic than the idea of orbitals, are still very, very important to us at the grade 12 level, because when we get into drawing complex molecules, we will always start with that Lewis diagram that we know how to make, and I will review to you how to make them. Because it's that Lewis diagram that then allows us to think about what's happening to their orbitals. So we will still be using Lewis diagrams to act as a starting point when we are solving these problems, analyzing a structure. So, atoms want to get a full outer shell. That's still the case. So we're going to be dealing with ionic bonds today. Again, just like last year, I'm going to show you an example. We'll run through a handful of other examples, just like we did in the past, except now we can talk in terms of orbital, energy level diagrams. We're not going to worry about orbital views yet. We're not going to worry about the shapes and all that stuff. We'll get into that when we do covalent. So again, very much a reminder of the stuff that we learned last year. Ionic bonds take place if there's a high delta En. Again, recall electronegativity is that number. It's on our periodic table. It's a number that kind of relates how well an atom is, or how good an atom is at sharing its electrons. High electronegativity means it has a strong pull on that pair of electrons in that bonded scenario. If we've got a great difference in the electronegativity, then it's not a fair fight, and the one with the high electronegativity is pulling that electron or pair of electrons away from the other atom. We had our bonding continuum from 0 to 0.2. We called it nonpolar. From 0.2 to 1.7, we called it a polar covalent bond. and anything with a delta En greater than 1.7, we called that an ionic bond. Complete transfer. So why do we have this transfer? A metal with a low electronegativity, an S-block metal. So the low electronegativities are over here. They tend to be S-block metals. They tend to lose their valence electrons to a non-metal with a high electronegativity, and they tend to be these P-block nonmetals. Okay, so now let's just run through a few examples. This is exactly the same as last year. This Lewis diagram representation is very much review, but on the next slide we will do an energy level representation so we can see what's happening on an orbital by orbital basis. And this is nothing new. We're dealing with sodium. Whoops. Oh, I don't have, the smart thing is not running. I should have observed that. All right, you guys can get started that one. That's the N with 1 dot, the fluoride with 7 dots, transfer the 1 over, square brackets, et cetera, et cetera. I'm going to just attempt to fix this thing. I gotta close it all. Okay. Oops. Now what have I done? All right, all's well. Okay, so hopefully you've done this up ahead of me. So this is the classic what we did last year, Na 1 dot F 1, 2, 3, 4, 5, 6, 7, right? We have that transfer of the sodium's electron to fluorine, and it results in an Na plus and an F 1, 2, 3, 4, 5, 6, 7, 8 minus, all right? Lewis diagrams, even though they're a little more simplistic than what we know now in terms of orbitals, are still the fundamental way in which we represent molecules. This is true all the way through chemistry. So right to the top level, if somebody's drawing a molecule, they're drawing it using a Lewis diagram, and it's because they work so well. And so we do really need to be able to understand these and draw them. The main important parts in terms of ionic compounds is that if you've got a charged ion, whether it's a polyatomic ion or whether it's a very simple ion, you put the square brackets around it. Actually, I've got it wrong here. That plus charge should be on the outside. Same with the negative ion, and you've got to include all those electrons so that we have our electrons kind of totaled up. I kind of stumbled upon this just as an example with the grade 11s this year. I didn't state it for you guys last year. Remember last year when we were doing the more complex ones, we total up all of the valence electrons and then we start to build the structure. I'll be reviewing that in a few lessons, but it's the truth here as well. If we take a look at our valence electrons, 1 valence electron for sodium, 7 valence electrons for fluorine, and when we're finished our Lewis structure, there must be the same number of valence electrons in that Lewis structure in total. So we've got 8 valence electrons to begin with, And if we total these valence electrons up, you'll notice there are 8 valence electrons there as well. You guys were pretty strong at this stuff, so you're probably looking at me and saying, well, of course there is, Ms. Sanders. That's the only way you can draw that. And that's true. But I sometimes come across students that just want to put electrons wherever. They want to load this one up too because they think the shell is full or something like that. But in the end, the number of valence electrons you had at the beginning must be the same as the number of valence electrons that you're drawing in your Lewis structure. So in this case, 8. So the quantum view, or the energy level view of this particular thing. So we're essentially looking for the energy level diagram. Now this can be kind of drawn out and long-winded, but it's important to see where these electrons are going. So in this case, I'm going to draw an energy level diagram for sodium, and I'm going to be drawing an energy level diagram for fluorine. And so sodium, and I'm going to do a core diagram. So sodium, I'm going back to neon, Ne square brackets. Now these square brackets are different than our square brackets for Lewis diagrams. They just represent the core, all right? And it doesn't represent concentration now, right? So our square brackets have different meanings depending on where you're using them. And if we go ahead from our neon, we get to, what is it, a 3s? We get to a 3s, and it's got 1 electron in it. And so there is our energy level diagram for sodium. For fluorine, we're going to go back to helium, He, and that brings us then to 2s, which we can see is full, all right? And it also then brings us across to 2p, which has 1, 2, 3, 4, 5 in the p. And there's our 7 valence electrons. And in the formation of the ions, and I hope you can see this, we're going to have that particular electron go into that spot. All right? Now you might notice that I've got the electron in the 3s pointing up. You might think that that's a +1/2 spin. And in the fluorine, the box it's going into also has arrow up. And that's because I always start with arrow ups, arrows up. I always start, 1 is up, 2 is down. I think I start with up because I'm such a positive person, right? I always have that positive outlook on life. So I always start with the up. That's just what I believe anyway. I think that's the case. In actual fact, if that electron were to be transferred, and let's say it truly was the wrong spin, because it could be that it's spinning parallel to that other one, then there would have to be what we call as a spin flip. There would have to be a flip at some point. And electrons do that all the time. Electrons in a real scenario, if they need to pair up and they're both spinning the same way, one of them will flip. Now, that takes energy. That costs a very tiny bit of energy. It's really like an electron jump. When you take any electron and change its quantum number, and that's what an electron jump is. Remember when we were talking about how they can jump from one orbital to another orbital and that gives off light? I didn't even talk about how that kind of translates over into the quantum idea, the quantum world. But if you take an electron and you move it from, say, a 2s orbital, and it's going to get excited, and it's going to jump now up to a 3s orbital, then that takes energy. That's a good old classic jumping from the second energy level to the third energy level. But now we can have even sub-level jumps. You could excite an electron from the 2s orbital up to the 2p orbital. So you can make a tinier little jump. It just means it involves a little bit less energy because you're not jumping an entire energy level this time. And you can even make a smaller little energy jump. If you give an atom just a tiny little bit of energy, you can get an electron to flip, all right? The lone electrons are the only ones that can do a spin flip, all right? But you can do it. A tiny little amount of energy can cause an electron to flip. It costs a very tiny amount of energy. It's a very, very small electron jump, but it still is an electron jump, all right? So now our idea of electrons jumping different orbits have now become a little more complicated. in that they can actually jump from an S to a P, right? Or they can even just go from a spin plus 1/2 to a spin minus 1/2. Yep. Yep. Well, it's going to give off, that's an interesting way of looking at it. That's an interesting way of looking at it. When a chemical reaction takes place, we already know that it's either endothermic or exothermic. And when you form something like sodium fluoride, that's going to be an exothermic situation. And that's because the energy given off by the electron getting nice and close to that fluoride or fluorine nucleus is greater than the energy needed to take that electron away from the sodium atom, right? So the energy given off is greater than the energy needed. That's what makes it exothermic, all right? And your question is the reason for that because it's going from a 3 to a 2? I don't think I can say no to that. I don't think it's as simple as that, but it's not a bad way of thinking of it. If the electron is in the third, it's going to be further away from the nucleus than the electrons as it lands into the 2. And if you're being pulled away from something that's further away, that's less energy because the force is weaker. And if you're being sucked into something that's closer, that's more energy being given off because it is closer. So that's not a bad interpretation of it, all right? In the end, it's going to fall back to our idea of ionization energy and electron affinity, but that's not a bad way of looking at it. To be honest, I've never thought of a formation of an ionic compound as an electron jump from an orbital in one atom down to an orbital in another atom, but I don't think there's anything wrong with that interpretation. It's a neat interpretation. I've never thought of it that way before. So I would say yes to maybe on what you said. Is that why we're getting that energy off because of that jump down there? Sure, yeah, that would be a source of the energy. I would agree with that. All right? So the spin can flip, all right, and that's not a big deal. In the end, I'm going to draw what happens in the end. Now I've got an Na plus, and it's going to look like neon. And here I've got an F minus, and it's also going to look like neon at this point, but I'm going to draw it out as if it's full so we can see what's happened here. So I'm going to have my helium. I'm going to have my 2s. I'm going to have 1, 2, 3, 4, 5, 6. So it's full right now. And essentially, there's our energy level representation of a formation of an ionic compound. All right. I just want to mention an application of this spin flip situation. How many people have had an MRI done before? MRI. You just one? That's cool. Knee? No? Head? Oh, that's exciting. Head. Not even going to ask what they're looking for. They're not very fun, right? Because you're right in there, right? And the magnet's making all kinds of noise and all this type of thing. An MRI, what an MRI does is it takes into account the energy, the tiny little bit of energy that's needed to flip the electrons in all of the hydrogen atoms that are in our body. In university, an MRI is obviously a medical imaging piece of equipment, but it originated from chemistry, all right? And from chemistry, it's called why can't I think of what it's called? This is terrible. I use the equipment all the time. It's not MRI. Magnetic resonance imagery, that's what the MRI is. I can't think of the name of the darn thing. That's terrible. I got to go back and check that. Anyway, same type machine, except it wasn't really big for people to go in. It was like shaped like a big Tic Tac. Yeah, like a Tic Tac. You know, it was white. And you'd open the door in the front, and you'd put your sample into the middle of this, which is where the magnets were, and you'd close the door. And then you'd I'd have to leave the room because anybody with prosthetics had to leave the room because when it turned on, it was like my leg would have stuck to this machine because it was like a super magnet, and that's what it is. It's super magnetic. If this was at the beginning of bank cards, and if you forgot to take your wallet out of your pocket and you ran the machine, all those strips would have been toast because it would have just changed the magnetic orientation. Anyway, here's what an MRI does and this other machine, which I can't think of the stupid name. In all of our hydrogens, right, there is one electron. And if you turn on a strong enough magnetic field, you can get all of those electrons to line up in all the same direction. So if you go into an MRI and they turn it on, what happens to all of the electrons in your hydrogen atoms is they all line up together. Because under normal conditions, they're all in random directions. That's for the visual learner. That means random. That's chaotic, okay? All right. Turn on the MRI, turn on the super strong magnet, and all of them line up because those spinning electrons behave like little magnets, so you line them all up with the magnetic field. And then what happens is when you shut that magnet off, the electrons begin to kind of go back to where they were spontaneously. It's just like when you shine the right colored light on an electron and it does an orbit jump. Remember the good old orbit jumps? After a short amount of time, they automatically fall back down and they give off a little bit of light. The exact same thing happens with the electrons. You line them all up, and then randomly they go back to their original level with whatever spin they were at. If they were already at +1, they wouldn't fall back down, but if they were at, +0.5, if they were at -0.5, they'd flip back down to -0.5. Anyway, and that gives off a very little bit of low energy light. It's so low it's in the radio wave range. You wouldn't be able to see it, but you could catch it with proper antenna. And that's what they're catching. They're catching the little bits of light that are coming from the electrons going back to their original orientation. And from those little bits of light, they can make an image of all the tissue because of all of the little bits of light coming from it. So that's the way an MRI works. It works on lining up the spin and then letting that spin transition back to where it is. So it's simply a little spin transition that it's using. Okay, let's do another example here, a couple more, and then we will let you do some examples and some questions. And then actually I have a video to show you. I found, so this Friday we'll watch a video maybe here. So again, go ahead. I'm going to do a Lewis diagram, and then I'm also going to do an energy level diagram. You can just go ahead of me if you get the idea. But again, this is very straightforward. So Mg, right? We've got 1, 2, Cl, 1, 2, 3, 4, 5, 6, 7. So I'm going to need 2 of those guys, right? Remember this good stuff here? It's going to result in, and I'm going to put the Mg in the middle, plus 2, Cl, 1, 2, 3, 4, 5, 6, 7, 8, minus 1, Cl, 1, 2, 3, 4, 5, 6, 7, 8, minus 1. I suppose you could put a big 2 and put 2 Cl. Textbooks, though, the way they like to do it, even university level 1, they like to see that, individual ions with them kind of arranged in some kind of logical fashion. Because again, it's supposed to be simulating or representing the lattice structure. So here we've got a repeating sets of 2 Cls with 1 Mg and 2 Cls with 1 Mg. In terms of the energy level diagram, these are going to become quite complicated. And when I give you some examples, I don't need to see all of the energy level diagrams, but it's good to see them here. So I'm going to need 2 Cls, and I'm going to flank them with an Mg just to kind of, so I can distribute the electrons. So the chlorines, we're going back to neon, and it looks like we've got 3s and 3p. 1, 2, 3, 4, 5, 6, 7. And down here the same thing, neon, 3s, 3p, 1, 2, 3, 4, 5, 6, 7. And the magnesium, we're going back to neon as well. and it just has 3s. 3s, 1, 2. So we will have one of the electrons in that spot and one of the electrons in that spot. In the end, what does it form? It forms a Cl minus. And just for some speed here, we do see now where it's coming from. So just for the sake of some speed, that's going to become the same as argon. It's going to have the same electron configuration, the same energy level diagram as argon, because we've now gained one. Yep.
Because like, you know, if you use like square bracket, it's like you're going up to like the double gas, right? Like,
Yep.
when you see it, like the one that's like next to it,
Mm-hmm.
like,
Means it's isoelectronic to it. Yes. Yep. It's the whole thing. That's what it is. Yep. So yeah, instead of drawing this whole thing just for the sake of speed, because I'm going to be doing more examples, it's the same as argon. Yep. And this one here, Mg, we're going to go back to neon. So it's going to be isoelectronic to neon, and that's going to be a +2. And this chloride minus is going to be isoelectronic to argon. Okay? I think we get the idea here, so I'm not going to drag out anymore. I was going to do another example, aluminum and iodine. Oh, I'm going to need 3 iodines for the aluminum because aluminum has 3 electrons. I'm not doing that. Let's talk about properties of ionic solids. The video I found has our good friends from MIT from 1970s. Blue to red, as said, right? So I want to get to it. See if we come up with any other ways of thinking about bonding. So just like last year, I finished off this quick little note on ionic compounds with properties of ionic solids. The ions that make up the ionic solid are arranged in a specific array. This time I've used the term array. It doesn't matter. We called that a lattice structure last year. Same thing, repeating units which result in the formation of crystals with smooth, shiny surfaces. Did anybody take the Earth and Space Science last year? You made some crystals last year, probably? Yep, good stuff. You can take entire courses. You can get entire specialist degrees in crystallography, the study of crystals. I didn't take any geology courses. You'd have to ask Mrs. Murray, but I'm pretty sure they study crystals quite in detail there as well. Study of different minerals naturally occurring in the Earth's crust, et cetera, et cetera. Yep. There are a few practice problems that go with this. If you're not back, they'll be online or on the movie. Okay. The units of ionic compounds cannot be easily separated, as an ionic bond is very strong. We've talked about that last year as well. That three-dimensional structure behaves almost like scaffolding. We know what scaffolding is? See it on the outside of buildings, workers on it, right? It's got all these cross beams and all these different structural parts to it so that if there's force put on one edge, then there are always structures holding it back in that opposite direction. So it doesn't matter what direction you push, there's always something pushing back. That's true for an ionic solid as well. You try to take an ionic crystal between your thumb and your finger, you try to squeeze it. You're not going to just push it over, it's going to maintain its shape. It's not like a molecular substance, like a piece of wax. You put a piece of wax between your thumb and your finger and you can just easily deform that. That indicates that in that wax structure there's not the same regular repeating structure that then supports the structure. Ionic bonds can be broken when the ionic solids are melted or shattered, right? So if you were to take a salt crystal, maybe put it between two spoons and crush it, you would then break those bonds. Again, information that's reviewed from last year. The ions in ionic solids are not free to move in the solids, therefore they're non-conductors of heat and electricity. But in the molten state and in solution, the ions can move freely, so electricity and heat can be conducted, and we say they're electrolytes. Okay, so the old textbook did not have any examples in it for ionic compounds, so I just put them up there. But the new textbook did have just a very few, 1 to 3. So I'll leave that up there. Again, you don't have to necessarily draw the energy level diagrams. You might want to draw it for one of them, make sure that you can do such a thing. For the rest of them, you probably want to just do the Lewis diagram so that you're back to thinking about Lewis diagrams and how we're representing electrons and ions, et cetera, et cetera. So I would do maybe the energy level diagram for one of them, maybe lithium and sulfur or something like that, just so that you can do it. And as you're doing that, I'm going to get this video stopped so that we can, because I've got to disconnect my